Researchers recently published a room-temperature photonic Ising machine that processes over 200 billion operations per second. It stays stable for hours without cooling or maintenance. It solves max cut, number partitioning, and protein folding problems that can still overwhelm modern supercomputers in general form. This isn't a GPU or a quantum. It's something fundamentally different, specialized optical hardware engineered from the ground up for a specific class of problems that matters across cryptography, logistics, and drug discovery. The catch? It only works if your problem fits the Ising model. Get that wrong and you've got an expensive paperweight. But get it right and you're exploring solution spaces at speeds that conventional compute can't touch. NP-hard combinatorial optimization problems are everywhere in industry and science. Route planning for delivery networks trying to minimize fuel costs and time, manufacturing schedules across distributed factories, graph partitioning for circuit design and network topology, protein folding for drug discovery and molecular design, research allocation and data centers. These aren't theoretical toys that only mathematicians care about. They're the problems that cost billions of dollars in inefficiency every year across logistics, telecommunications, pharmaceuticals, and finance. Conventional computers approach these problems through heuristics and approximations. They don't check every possibility exhaustively. That would take longer than the age of the universe for problems of meaningful size. Instead, they use smart search strategies, local optimization techniques, and pruning methods. But here's the fundamental issue. The search space still explodes exponentially as problem size grows. A problem with 100 variables might have up to 2 to the power of 100 possible solutions. That's 1.2 nonillion solutions, and please tell me, when's the last time you heard a word nonillion? That's more than a septillion combinations. Even with heuristics cutting the search space dramatically, the computational burden scales very poorly. Supercomputers hit scaling limits fast. The Ising machine works on completely different physics. Instead of checking possibilities through approximation algorithms alone, it maps your optimization problem into an energy landscape. Think of it physically. Every possible solution to your problem is a point on the landscape. The height or energy value at that point represents how good or bad that solution is. The best solutions sit in the deepest valleys. Worse solutions sit on higher ground. An Ising machine is engineered to search that landscape and find those valleys. What makes this powerful is parallelization through physics. Billions of interactions happen simultaneously, all pushing the system towards lower energy states, all exploring the landscape in parallel rather than sequentially. A conventional computer checks one path and then checks the other. An Ising machine, on the other hand, explores many paths at once through optical and electronic interactions happening at light speed. It's not smarter than a GPU. It's fundamentally different to it. It's physics doing the optimization work instead of logic gates executing algorithms. Now, this isn't a semiconductor chip. This isn't something you'll see in a consumer product anytime soon. What the researcher team built is a tabletop photonic computing system constructed from the off-shelf telecommunication components. Cascaded thin film lithium niobate modulators, semiconductor optical amplifiers, a digital signal processor running a feedback loop. Light carries the computational signal. Electric fields modulate that light based on problem parameters and feedback. The system iterates through cycles powered by optical propagation speeds and electronic feedback. Room temperature operation is critical to understand. Quantum annealers, which also solve Ising-type problems, require dilution refrigerations that cool the system to near absolute zero. They need constant constant maintenance. They need shielding from vibration and electromagnetic interference. This photonic system runs at your desk. No exotic cooling infrastructure, no quantum decoherence where quantum states become unstable and lose information. No finicky calibration between experiments. Just photons bouncing through an optical loop, getting amplified and modified cycle after cycle, converging towards solutions. The programmability comes from the digital signal processor. Different optimization problems get different control signals sent into the optical system. The system adapts. Time encoding signals represents variables and their interactions. This is a clever trick that will let a physically compact system handle problems with tens of thousands of spins without requiring billions of individual optical channels. Instead of having one optical path per variable, the system multiplexes the problem across time. Different time slots represent different variables and couplings. This is how you solve a 41,000 variable problem with a tabletop system instead of requiring a room-sized optical setup. The performance metrics matter because they're what separates genuine capability from marketing hype. The system delivers over 200 billion operations per second for the core computation in the optical domain. That 200 GOPS number represents the throughput for spin coupling and non-linearity calculations, the fundamental operation the optical system executes. On fully connected problems where every variable connects to every other variable, the system handles up to 265 spins. With 265 binary variables fully connected, that creates 65,536 couplings, the interaction terms between variables. That's substantial, but not massive. The real scaling advantage appears with sparse problems, where not every variable connects to every other variable. On sparse graphs, the system handles 41,209 spins and 205,233 couplings. That's a massive increase compared to the fully connected case because you're only encoding interactions that actually exist in your problem. You're not wasting computational resource on couplings that aren't there. The feed-forward latency, the time for a single pass through a computation loop, is approximately 4.1 microseconds on the largest test case. That's 4.1 millionths of a second. In their current lab setup, reported time to solution for large max-cut instances is on the order of tens of seconds, while pipeline DSP estimates indicate sub-millisecond time to solution for the same iteration counts. The difference between measured lab results and pipelined estimates matters because it shows where engineering optimization could improve performance. Room temperature stability for hours of continuous operation is verified and documented. No cooling cycles, no thermal drift that gradually breaks the system, no maintenance between runs, just reliable operation and ambient conditions. The research team didn't just build hardware and make theoretical claims. They ran benchmark on 3 established problem classes that have been studied extensively in computer science. The results matter because they demonstrate capability on real problem types, not just toy problems created to make the system look good. MaxCut in arbitrary graph topologies is the first benchmark class. MaxCut is a classical NP-hard problem fundamental to graph theory and optimization research. The goal is to partition a graph into 2 groups so that the number of edges connecting between the groups is maximized. As graphs grow, finding true optimum becomes exponentially harder. The team demonstrated this in graphs with 2,000 spins, then scaled it up to 20,000 spins. For each problem size, they showed that the system converged to good solutions reliably in consistent timeframe. This represents capability beyond what photonic Ising machines have previously demonstrated. Numbered partitioning is the second benchmark class. The problem is to divide a set of numbers into two subsets so that the sum of numbers in one subset is as close as possible to the sum in the other subset. It's canonical NP-hard problem that appears in cryptography research, bin packing algorithms, and resource allocated theory. It's been used as a standard benchmark for optimization systems for decades. The fact that this photonic system handles it well signals capability across multiple problem types. Lattice protein folding is the third benchmark, and it's particularly significant. Protein folding is computationally expensive and fundamental to drug discovery and biological research. Finding the ground state of protein models on lattice is NP-hard in the general case. This is new territory for photonic Ising machines. Previous photonic systems hadn't demonstrated solving protein folding problems. That represents a new capability claim and suggests that the system can handle biological problems that previous approaches couldn't even tackle. This is a hardware breakthrough in a category most people ignore. Optimization problems aren't sexy. They don't trend on social media, but they cost industries billions of dollars in efficiency. If this scales from labs into deployable systems, it reshapes how companies solve logistics, network routing, drug discovery, and cryptographic workloads. The breakthrough isn't in artificial intelligence or intelligence at all. It's the photonic computing that is becoming stable and programmable enough to tackle specific problems classes at meaningful scale. That's material science and engineering paying off. Light-based hardware that actually works in real conditions, not just theory.